For over a decade, data architecture has been built on a foundation that is starting to fracture under its own weight. We trained an entire generation of engineers to default to distributed cluster computing, spinning up heavy Apache Spark clusters or Snowflake instances, whether they were processing petabytes of logs or just a few gigabytes of clean data. This one-size-fits-all approach forces every simple analytical query through a gauntlet of network orchestration, creating unnecessary latency and driving up cloud bills. A leaner approach to system design has emerged to replace it: the Duck Stack, built on three pillars: DuckDB, Duck Lake, and MotherDuck. Instead of treating every query as a distributed system problem, this stack combines embedded columnar processing with cloud-native hybrid compute. The result is the ability to query gigabytes or petabytes of data with sub-second latency, bypassing traditional infrastructure overhead and cutting cloud bills by as much as 80%. To understand how this works, we need to deconstruct the stack from the ground up, starting with the in-memory execution engine, moving to the storage layer, and scaling out to the cloud. We are going to look at exactly how petabyte-scale lakehouse analytics is being decoupled from the traditional distributed cluster model. The foundation of this architecture is DuckDB. You can think of it as the SQLite for analytical processing, or OLAP. Look at this system architecture. The defining trait of DuckDB is that it is a single, self-contained binary embedded directly inside the application process, whether that's Python, R, Node.js, or even a web browser. Notice the complete lack of external network lines. Traditional databases require deploying and configuring background server processes to handle requests. DuckDB completely eliminates that operational burden. Embedded accessibility is only half the battle. To be viable, the engine has to be fast, which it achieves through a vectorized execution model. This diagram illustrates the difference. On the left, a traditional model scans sequentially, row by row. On the right, DuckDB groups data into blocks, passing chunks through the CPU simultaneously. By chunking data, it leverages SIMD instructions, executing one mathematical operation across every data point simultaneously. This approach drastically reduces the total number of CPU cycles required per query compared to those older row-based iterators. By removing network latency entirely and maximizing physical CPU efficiency, DuckDB brings data analysis back to the bare metal of the host machine. Running analytics locally immediately presents a physical constraint. What happens when the dataset is larger than the machine's available RAM? DuckDB handles this through out-of-core processing. It intelligently streams data directly off the local disk or cloud object storage in carefully managed chunks. This streaming architecture ensures the engine only holds what it can process, explicitly preventing the out-of-memory crashes that typically plague local data workflows. Once the data is processed, it still needs to be handed off to other local tools like Python or Polars. In traditional pipelines, serializing and deserializing this data creates massive bottlenecks. The solution is zero-copy data transfer, which integrates natively with Apache Arrow. This visualization shows a single block of Arrow-formatted data in memory. Instead of duplicating the block, both DuckDB and Python reference the exact same memory location via pointers. There is no copying, no moving, and no serialization delay, which enables query pipelines to execute instantly across different environments. Through out-of-core streaming and zero-copy mechanics, a standard laptop can comfortably and safely manipulate data volumes that previously required a dedicated server farm. Local execution is solved, but accessing massive data on cloud storage requires an open table format. This brings us to the lakehouse layer. The current industry assumption is that modern lakehouses must use distributed formats, specifically Apache Iceberg or Delta Lake, to manage their metadata on object storage. These legacy formats suffer from a critical flaw known as the small metadata file problem.
On the left, a legacy format generates thousands of tiny manifest files. The query planner is forced to crawl this exponentially branching tree. Parsing this sprawling hierarchy introduces severe latency, waiting on hundreds of network requests just to retrieve data. To keep the system functional, data teams are forced to run constant, resource-intensive background compaction jobs just to clean up the metadata. Furthermore, these table formats track state in complete isolation. They fail to support atomic, multi-table transactions across entire database schemas. By improperly treating object storage as a transactional metadata catalog, standard open table formats essentially recreate the very database latency they were designed to avoid. To strip away this operational friction, the founders of DuckDB introduced Duck Lake. Duck Lake makes a strict architectural decision. On the right, watch how Duck Lake decouples Parquet data from its metadata. The query planner bypasses the object storage hierarchy, sending a single query to a highly indexed transactional relational database. Finding the relevant files drops from a slow network crawl across object storage to an indexed SQL query executed in milliseconds. Duck Lake introduces data inlining for streaming events. Continuous data inserts flow directly into the relational database catalog. Once a threshold is met, the database flushes the data out to object storage as a single large Parquet file block. By storing these micro-batch writes inside the catalog until they hit critical mass, the architecture completely eliminates the small file problem. Because the metadata rests on a relational foundation, it natively supports atomic, multi-table ACID transactions across an entire database schema. And while it is optimized for DuckDB, Duck Lake remains entirely engine agnostic. Any engine capable of standard SQL can read or write to the catalog. By moving metadata back to a relational database where it belongs, Duck Lake delivers the massive scale of open cloud storage with the transactional speed of a traditional relational system. This leaves us with a final hurdle. If DuckDB executes locally and Duck Lake stores data in the cloud, how do we process massive aggregate queries without bottlenecking the local machine's bandwidth? The answer is MotherDuck, a serverless enterprise cloud platform built specifically to wrap around DuckDB and Duck Lake. MotherDuck's hybrid query execution intelligently splits the SQL query plan. Massive table scans and aggregations are assigned to a blue cloud node, compressing raw data into a tiny result set, which streams down to the green local machine for final filtering. By only moving the compressed results back over the network, the local machine receives exactly what it needs to perform the final lightweight filtering instantly. MotherDuck also provides fully managed Duck Lake infrastructure, letting engineering teams instantiate petabyte-scale lakehouses with zero ops using standard SQL commands. Organizations can utilize a bring-your-own-bucket model, keeping their actual data completely secured in private cloud buckets, while outsourcing only the compute and cataloging layer. Hybrid execution silently pushes the most demanding workloads to the cloud, allowing a local laptop to process massive datasets without taxing its own hardware. When these layers lock together, they form a frictionless data architecture. This breaks down the complete end-to-end data platform built on the Duck stack. We move across 4 stacked layers, from ingestion to lakehouse storage, up to compute, and finally to data serving. Ingestion pipelines stream data directly into low-cost object storage, organized by Duck Lake. The workloads are processed locally by DuckDB, or scaled to MotherDuck, natively serving business intelligence tools and AI agents through the Model Context Protocol. The stack successfully unifies the low-latency iteration speed of local development with the petabyte scale of cloud storage. The Duck stack marks a pragmatic return to engineering simplicity. It eliminates cluster orchestration, cuts cloud expenditures drastically, and proves that massive analytical workloads no longer require massive infrastructure bloat.